Today we're going to start talking about solving log and exponential equations, and I'm going to break this section into two parts. So basically for part one, we can take a look at some more simple equations and focus more on the process, and then in part two, we'll look at some of the more complicated equations. So basically when I say today we're going to be looking at some of the more simple or basic equations, I mean we're going to take a look at equations that have just one single log or exponential function in it. You won't have an equation until part two where it has like log here and a log over here, or two different exponentials or something like that. We're going to be focusing on just one for today. Now, what's good is it doesn't matter which one it is. It doesn't matter if it's a log or an exponential. Basically, we're going to follow the same steps to solve. So, to solve an equation that only has one single log function or one single exponential function in it, this is what we're going to do. Number one, you have to isolate it first. And I said this is very important. If you try to do step two, what I'm about to tell you, when it's kind of mixed in with some other numbers, it doesn't work. But once it's isolated, we're just going to switch it. And this is why I said it doesn't matter which one it is, because if it's a log equation, we're going to change it to exponential. Or if it's exponential, we're going to change it to log. And what happens is usually just by changing from one form to the other, it almost solves itself. Sometimes there's a couple extra steps at the end, but you're usually pretty much done just by changing. Now you do want to solve, and like I said, there's usually one or two simple steps at the end, but it's changing from log to exponential that pretty much solves it for you. So before we do an example, I want to talk to you about what are called extraneous solutions. And you may have seen some of these in a math class before. This is the first time we've talked about them this year. An extraneous solution is an incorrect answer that shows up in your work even though you didn't do anything wrong. It's just a certain thing that happens in certain types of math problems. So you can do the work perfectly correctly and still get a wrong answer. So you need to know when that can happen, and when it can happen, you need to go back and check your answers and make sure you didn't get one. So even though it's not the one we're talking about today, let me quickly talk about a different one, a different common one. Extraneous solutions happen when you square both sides of an equation. So that's something you want to remember. It's not what we're doing right now, but it's a good thing for you guys to remember. If you're ever solving an equation and you square both sides of the equation, at the end of the problem, you have to go back and check your answer. And the reason is squaring an equation can make something that is not true look like it is. For example, if I said -1 equals 1, then you'd go, no, that's not true. And you're right, it's not true. But if I square both sides of the equation, now you get 1 equals 1, and it's true. So squaring an equation can take something that's not a true equation and make it look like it is a true equation. That's where extraneous solutions come from. Now, log equations also can give you extraneous solutions. It's different, it's not the same as squaring, but you can. And a log extraneous solution might happen something like this. Let's say you had an equation that had log of x in it, log of x equals something. And you do some work, and you get to the end, you do the work perfectly, and it tells you the answer is x equals -5. Well, the problem is, if I put -5 here, what I get is the log of -5. Now, one of our properties of logs, you can't take the log of a negative number. That's the reason why log equations can give you extraneous solutions. So if you ever get to the situation where the x value that you solve for, when plugged in, gives you the log of a negative, then you throw that answer out. That's extraneous. Now, you don't know when it's going to happen, and it doesn't mean you did something wrong, but it does mean that every time you solve a log equation, you have to go back at the end, plug your answer in, and make sure it works. Now, you don't need to do that for exponentials. For an exponential equation, they do not have extraneous. You can check your answer. I mean, it's never a bad idea to plug your answer in because it's a good way of checking to make sure you get it right. but you have to do it for log equations, because even if you do the work perfectly, sometimes they give you an answer that doesn't work. All right, so here's our first example for today. This is an exponential equation because I have a 3 to some power. This is an exponential function. I can see it. It's the one in parentheses right there. Which means when I solve, I don't have to worry about extraneous solutions. It's not going to happen on this one. So let's get to solving. It was a very simple 3-step process. Number 1 was to isolate the function, whether it's a log function or an exponential, get it by itself. So basically the one in the parentheses, the 3 to the 2x minus 5 power, I just need to get that all by itself. So let me start by adding 3 to both sides. I want to get rid of that 3. Cancel that out, and I have 2 times 3 to the 2x minus 5 equals 14. Now, before I do the next step, let me tell you something you can't do here, because people do this all the time. They multiply. They go, okay, so 2 times 3 is 6, so I have 6 to the 2x minus 5 equals 14. That's wrong. And you can never multiply something that does have an exponent with something that doesn't. They have to remain separate. So we do not want to do that. Let's get rid of that. What we want to do instead is get rid of the 2 by dividing. If you have a 2 in front of your exponential function and you want it gone, just divide both sides by 2. So now I have 3 to the 2x minus 5 equals 7. Now, if you remember from a couple sections ago, we talked about how to switch back and forth from log and exponential form. And I showed you 2 ways to do it. If you forgot them and you want to review, go back and watch that video again. What I personally like to do is use inverses. So if I have a 3 to the x and I want to cancel it out, I do that by taking the log base 3 of both sides of the equation. Because the log base 3 and the 3 to the x will sort of cancel each other out and just leave you with the exponent, which is 2x minus 5. And 2x minus 5 equals the log base 3 of 7. Now, when you get to this point right here, when you get to log base 3 of 7, here's what I want you guys to do. If it's something that goes cleanly, like if that said log base 3 of 9, then you could just make it a 2, because that's what it is. 3 to what power is 9? 2. But when it's something that doesn't work cleanly, like this one, log base 3 of 7, just leave it. I don't want a decimal answer. I don't want you to use change of base in a calculator and round it off. I want you to just leave it as the log base 3 of 7. Now, to finish the question, we just need to solve for x. So 2 simple steps. I need to add 5 and divide by 2, basically. So let's do that. Let's add 5 to both sides. We'll put it on the end there. And I will move maybe over here. We get 2x equals log base 3 of 7 plus 5. And just like I showed you with the multiplying, remember when I said 2 times 3 to the 2x minus 5 does not equal 6 to the 2x minus 5? Make sure you understand that this does not equal log base 3 of 12. The log base 3 of 7 is one thing all by itself, and the plus 5 is completely separate. So don't add those together. This does not equal log base 3 of 12. But we can get our final answer by dividing by 2. And that's it. So the answer to this question is the log base 3 of 7 plus 5 all over 2. But basically the key was what I did in the light green there. When I got my 3 to the 2x minus 5 equals 7, when I got it isolated, I switched it to a logarithm that took that 2x minus 5 out of the exponent. So you can't solve for x when it's in an exponent. But once I took the log base 3 of both sides, it pulled it out of the exponent. Once I have that 2x minus 5 by itself, it was simple to solve. I just added 5 and divided by 2. All right, let's try a log equation. So another equation here, same direction, solve for x. Same situation, one single function, that's what we're doing for today. But this time it's a log function instead of an exponential. Last time we had a 3 to the x, this time we have a log base 4. But the question starts out at least the same. We definitely want to isolate the log function. So I'm looking at it, I'm thinking, okay, I have the log base 4 of x squared plus 6x. That whole thing together is my log function. To isolate it, I don't want that 5 in front of it. So let's divide everything by 5. Let's get rid of that 5 right there. So 10 divided by 5 is 2. And now we have the log base 4 of x squared plus 6x. So I isolate it. And now we want to switch it to an exponential. So remember, there's two ways to do it. I personally like using inverses. So if I want to cancel out a log base 4, I'm going to use an exponential base 4. And the way I do that is basically like this. I turn the equation itself into the exponent, and I do 4 to each power. So we have 4 to the second power, 4 squared, which is 16, equals, now remember the 4 to the x and the log base 4 cancel each other out, and just leave you with x squared plus 6x. So again, by changing forms, you've made the equation solvable. You can't solve for x when it's inside a log function. But when I changed it to an exponential, it pulled it out of the log function. Now I'm able to solve for it. Now it is a quadratic because I have an x squared term and an x term. So I would probably want to, well, I would definitely want to get it equal to 0 first. So let's start by subtracting 16 from each side. Minus 16. In fact, let me move it up here. And of course, when you get a quadratic, you have two choices. You can try to factor it if it's factorable. And if it's not factorable, then you go quadratic formula. This one looks like it is factorable. It looks like you could use plus 8 and minus 2. X plus 8 and x minus 2, because 8 times negative 2 is negative 16, and 8 plus negative 2 is positive 6. So your final answers for this one, actually it's not final, your answer for right now you get by changing the signs. You get negative 8 and positive 2. And the reason I said it's not quite your final answer is because remember, we have extraneous solutions, possibly. So you always need to check your answer for each one. So let's say, and when you're checking, you always go back to the very original problem. Go way back here to the original problem as it was. So let's start with the 2. The positive 2 is probably the easier number to use. So I have, if I plugged in 2, I would have 10 equals 5 times the log base 4 of 2 squared plus 6 times 2. And that would be, let's see, 4 plus 12 is 16. The log base 4 of 16 is 2, because it's, remember, logs are asking 4 to what power is 16. So I get 10 equals 5 times 2, and that looks fine. Yeah, that one works. So the 2 definitely works. Let's try the negative 8. Maybe I can squeeze that down here in the bottom. So I go back to my very original question again. And this time I'm going to have negative 8 squared plus 6 times negative 8. And that would be 64 minus 48. That's going to be 16 again. It's the exact same answer. So yeah, it does work. So both of these work. Once you've checked them, then you can box them up and say, yeah, those are both correct answers. But remember, one or both of those could have ended up being extraneous solutions. If one of them is an extraneous solution, throw it away and keep the other one. If both of them were extraneous solutions, then you would say no solution. This one has no possible answers. And remember, really, what you're looking for, what would make it an extraneous solution, is if you got a negative number here. That's really where the extraneous solutions come from. They will, if you're getting a positive number within your log, they will almost certainly always work out. It's usually, if you're going to get an extraneous solution, it might be because I got a negative 16 there instead of a positive or something like that. But basically that's it for today. Some nice simple one function equations just to get used to solving and to get used to this concept of testing for extraneous solutions. And then in part 2, we'll look at some more complicated, more complex, a little bit trickier equations to solve.